Hey, welcome back. My name is Chris, and if you're watching this video, you're here to learn about the Dji Agras series of agricultural drones. Now, in the last video, we learned about what agricultural drones can do. In this video, we'll learn about DJI's latest platform, the Agras T40. You'll learn what it's about, how it's an improvement upon previous iterations of the Agras lineup, and what makes it an excellent resource for crops everywhere. Ready? Let's take off. Now, the T40 has undergone numerous changes from the previous T30, the most visible of which is changing from 6 aircraft arms to 4, and changing from 6 motors and propellers to 8. Now, why do we do that? Let's take a look first at aircraft design. The early MG models had 8 arms and propellers, ensuring safe flight and landing if 1 or 2 of its motors malfunctioned. However, these propellers produced a thrust that was not entirely ideal for spray droplets to reach the middle and lower parts of tall crops. Why? The more propellers an aircraft has, the less thrust each individual propeller needs to achieve lift. This presents a challenge. How can we ensure flight safety with redundancy while reaching the ideal propeller force? To address that previously, we adopted a 6-propeller design for the T20 and T30. With the T40, we redesigned the propeller system by placing 2 sets on each arm, 1 on top and 1 below. With 8 sets of propellers on 4 arms, the T40 generates more thrust than previous models while providing flight safety if any motor or propeller is damaged. Dji Agras drones are designed to be foldable for ease of transport, which involves plenty of folding and unfolding. The early models had arm sleeves, which must be tightened each time the aircraft is folded or unfolded. To ensure safety, a user must check whether the arm sleeves were firmly tightened before launching the aircraft. The T40 features a folding buckle design which can be locked in 1 second and also includes a safety sensor. If the buckle is not locked in place, the aircraft will be unable to take off, therefore preventing crashes. Now let's talk about the spraying system, which perhaps has the most changes. In previous models, they use a pressurized spraying system which uses a pump to generate pressure. The fluid is then pushed and atomized through narrow holes in a sprinkler. The main advantage of the pressurized spraying system is that it is simple and reliable, but the flow rate is relatively small and the droplet size is difficult to adjust. The T40 uses a double-layer centrifugal spraying system which increases the flow rate to an impressive 12 liters per minute, 120% more than the T30. Its droplet size is also adjustable within a range of 50 to 300 nanometers. Centrifugal spraying systems are also better suited for spraying powder, based on the absence of small holes found in traditional sprinkler methods. With a greater flow rate and propeller thrust, the T40 works a lot more efficiently, especially when spraying on tall crops, such as fruit trees. Older DJI agricultural drones had radar sensors on the bottom, which allowed for omnidirectional obstacle avoidance. However, the drawback was that these sensors would often be covered or corroded by the droplets. With this in mind, the radar sensors are mounted on the nose of the T40. Binocular vision allows for automatic identification of obstacles in the front and calculates the best path to bypass them, horizontally or even over them. When there are suspended wires in the way, it can bypass them from above. Early agricultural drones are no different from others in terms of their individual flight control parts. Many of these are mounted individually, such as the IMU, flight control, compass, and GNSS. In fact, you can still see the GNSS as a top-mounted module on some aircraft. The benefits of this are obvious, for example, being able to replace individual parts if they become broken, but it does expose the issue of water control and damage. Flight operations require frequent refilling of spray chemicals. Therefore, to better protect the aircraft, we have placed all the flight control systems on the avionics panel of the T40. A unitary seal has also been added for waterproofing and corrosion prevention. This glue sealing technique to the T40's avionics panel is unique in the design of agricultural drones. The T40 aircraft has a protection rating of IP67. What does that mean? It means you can wash the aircraft with a water jet, and the aircraft is safe against strong corrosion from pesticides and chemical fertilizers. Besides its appearance and internal workings, what about the operating efficiency of the T40? I believe this is the #1 concern of many large farm owners and service providers. The T40's operating efficiency is mainly affected by 3 factors: operating parameters, stability, and load weight. The capacity of the T40 tank is 40 liters. At a consumption rate of 15 liters per hectare, and with a full tank, an aircraft can cover an area of 2.67 hectares. The maximum spray width is 11 meters, and the flight speed is about 10 meters per second. Two new designs have also been added to the T40 for better operating efficiency. One is the RTK signal maintained after power off module, which works like a small battery. When a battery is removed, it ensures the flight control module operates normally for a short time. After the battery is swapped, the user does not have to perform a satellite search again and can resume the previous operation immediately. Another design is a centrifugal spraying system, which minimizes blockage and ensures the continuous operation of the spraying system. Thanks to all these features, the T40 can reach an efficiency of 20 hectares per hour, up to 100 times that of manual labor. As we covered earlier, agricultural drones not only can spread liquid pesticides, but they can also spread solid pellets from 0.5 to 5 millimeters in size, and this includes grass and canola seeds, rice, and various fertilizers. It takes less than 2 minutes to switch a spraying tank to a spreading tank on an aircraft. The T40 has a capacity of 70 liters and a maximum load of 50 kilograms. One bag of fertilizer can be fully loaded at a time. After setting the spreading parameters, we can launch the aircraft to perform an autonomous mission, where it can spread 1.5 tons of fertilizers in just an hour. An aircraft operates less efficiently on orchards with steeper terrain than on other crops, because of the former's higher consumption rate, which typically reaches 150 liters per hectare. With a greater load capacity and flow rate, how productive is the T40? After 7 hours of operation, our aircraft has sprayed an area of 20 hectares at the orchard. Now, it might not sound like an impressive number compared to working on normal crops, but to produce the same coverage, a team of 30 people performing manual spraying would take 20 hours. As a plus, the T40 also utilizes pesticides more efficiently than workers in the field, preventing waste. Crop growth is affected by various factors such as sunlight exposure and soil quality. Even with the same field, the growth of crops can vary. So, how can we apply pesticides or fertilizers precisely? First, use the multispectral drone to survey and map the area, and then have the data analyzed through Dji Agras Intelligent Cloud, producing a prescription map. Using this map, the T40 will apply more fertilizer on areas showing weaker growth and less on those showing better health markers. In this way, we can reduce farming costs by allocating resources only where they are needed. So the prescription map is a great tool for farmers when deciding on pesticide usage, identifying pesticide and crop diseases, and even estimating yield. Modern agriculture has advanced from cruder and more traditional farming methods to those oriented to precision. New agricultural production tools are not only versatile, but also more efficient, intelligent, and environmentally friendly. Through precision spraying and spreading, Dji Agras drones have treated a cumulative 200 million hectares of land, reduced pesticide usage by 3,000 tons, reduced water usage by 87 million tons, which is the annual water intake of 150 million people, and reduced carbon emissions by 10.29 million tons, equivalent to planting 630 million trees. This is made possible by all the drivers, farmers, engineers, and partners who have worked together to bring a new lease on life to one of the oldest professions on Earth.